Okay, good morning, everybody. Welcome to this session. The first speaker of this morning session is Professor Feida Jiang from Southeast University. The title of the talk is Second Order Interior Estimates of Monge-Ampere type equations.
Thank you for the introduction and thank for the organizer's invitation. I'm very glad to attend this wonderful conference. And my topic today is the second order estimate of the Monge-Ampere type equations. And the focus is here is second order and also interior estimates. My talk will divide into three parts. The first two parts are just some historical review. So part one is an introduction of what is the Monge-Ampere equation and also their extensions. And part two, I will talk about the historical results on second order derivative estimates. Maybe some are interior and some are pure interior. And as the last part, I will talk about our results on some special kind of Monge-Ampere type equation. So let's move to the first part. This is the Monge-Ampere equation. That is the Hessian of a function u. Its determinant is given by a given function f of xu and gradient u. And it has a long history. Maybe the first mathematician is Monge in 1784 and Ampere in 1820, about 200 years ago. And the name first used is in the Sophie Slee's paper. He used the Monge-Ampere equation. But at first, this equation is studied in two dimensions, just like uxx times ux or uyy minus u, the square of uxy equals something. And the early treatment of this equation can be found in this book, Gusa. And in the 20th century, this equation is studied by many famous mathematicians like Minkowski, Bernstein, and Schauder, Levy, and many others. And its importance is because its relationship with geometric problems, such as the Minkowski problem and the isometric embedding problem, the wire problem, and also Calabi's conjecture is a complex Monge-Ampere equation. So I will talk about some generalization or extensions of this kind of equations. But I will only restrict the attention in the local version of the Monge-Ampere equation, in the real case, also in the Euclidean case. There are also many advanced theories in the complex Monge-Ampere case and the manifold case, group case, and the non-local case. I will not talk about in this talk. So there are three kinds of extensions of the standard Monge-Ampere equation. The first one is called the Monge-Ampere type equation, both the second order and the third order one. And the second group is the K-Hessian equations and their counterparts, and also their extensions. And the last one is the special Lagrange equation. Let's move to the first part, Monge-Ampere type equation, and the second order. Actually, this equation is the main topic I will talk about in the last part. So it has a more term here. That is Hessian of u minus a matrix. This matrix is a lower order term, A of x, u, and gradient u. and the right-hand side is still the same. But the application also related to optimal transport, geometric optics, and also conformal geometry. So this equation is more general. If A is equal to 0, it is a standard Monge-Ampere equation. And these applications can be found by Han Hong's book, and also Caffarelli's famous paper of optimal transport. And for the geometric optics, there is an open problem of STL in his book. And what's the fourth order? Fourth order equation has this form. The sum of Uij, and here is a standard Monge-Ampere operator, but it is a function, and it's a second order derivative. So totally, the derivative of U here is fourth order. One can divide them into a second order system. It is linearized Monge-Ampere equation coupled with the standard Monge-Ampere equation. And here is W, and this one is U. And this Uij is the cofactor of the matrix of D2U. And this kind of equation has already extensively studied, for example, by Nam Li and Bing Zhou. And the second group is K-Hessian. K-Hessian, it is this form. The SK operator equals F. And the SK is the K-Hessian operator. It is a case order elementary symmetrical polynomial given by this kind of function. So SK D2U is SK of the eigenvalue of D2U. So what is SK lambda? It is sum. It is the sum of the K product of these eigenvalues. So when K equals 1, SK is just the Laplace operator. And when K equals n, it is the standard Monge-Ampere. And in those SK, K not 1 and n, maybe just an integral between 1 and n. So it is more general. This kind of equation can be found in this review paper, the K-Hessian equation of Xujia Wang. And recently, there is a counterpart of the K-Hessian equation. This can be found in my paper with Julinger. We defined it in a reverse way. We call it the PK operator. So PK of D2U is a PK of its eigenvalue, and it is a product of the K sum. So just reverse these signs. And it is also interesting because in this case, if K equals 1, it is Monge-Ampere. When K equals n, it is Laplace. So it is another kind of operator. And moreover, when K equals n minus 1, this operator can be written in this form. And this one, now we call it n minus 1 Monge-Ampere operator, which is related to the Gaussian conjecture and the form type Monge-Ampere equation. So this one is studied extensively in recent years. And there are also many other kind of extensions, like the sums of K-Hessian, and maybe we can ask the sums of P-K-Hessian one important equation is called the Pogorelov equation. It is just a combination of sk, sk minus 1, and also the lower sk. Oh, sorry, here is also sk. A linear combination of sk. And an important theory is of cohesion is the quotient of cohesion. Maybe sk over sl equals f, and k is larger than or equal to l. And also, we can define this kind of function, pl over pk, but l is a small number and k is a large number. So these all these equations are elliptic in the sense of if the D2U are in a proper code. Okay, the last group is a special Lagrangian equation. It has this form, also a sum of z lambda. Okay, this lambda is also the eigenvalue of D2U, but it the form is arctangent lambda I. The sum of this equals to a number theta, and of course this theta should be in some range. We call this theta to be the face of the equation. So this equation is derived from the minimal surface theory and the Lagrangian geometry, which is introduced in this paper of Harvey and Lawson in 1982. Its solution of this equation describes calibrated minimal Lagrangian surfaces in complex space. And recently, this kind of surfaces has importance in the study of string theory. And it also related to those sk operators. If we rewrite this kind of equation, we can have this form. It is also a combination of these SKs. And we call this kind of equation is the algebraic form of the special Lagrangian equation. So if we write it in this way, we can see when this phi is particularly, and or the dimension is particularly chosen, this equation also reduced to the Laplace and determined Monge-Ampere and or S2 in different kind of situations. So actually, this kind of this SLE equation is a large series of equations, and there is a review paper by Yu Yuan. Its name is the special Lagrangian equation. And for these equations, maybe they are very similar because they are all described as eigenvalue operator of the eigenvalues. So let's move to part 2. Let's see the historical results on second order derivative estimates. First, let's see the result for this very standard equation. The determinant of D2U equals 1. So I list 3 kinds of results. The first one I call the pure interior second estimate. And the second one is if the dimension is higher, and we can construct the singular solution. So maybe for the singular solution, we don't have the interior estimate. And another one is if we can add a Dirichlet boundary value condition. And we can avoid this kind of singular solution. And we also have estimate. But this estimate is in a very special way, like this. So compared to the first result, we call it a Pogorelov type estimate because it is proved by Pogorelov in 1978. So let me explain what is the pure interior estimate. So we just consider this equation in a domain of Rn, and no boundary condition is assumed. And Haynes, in 1989 paper, he used a kind of characteristic theory. Okay, the main ingredient of this theory is something like a partial Legendre transform, which is first introduced by Darboux in 19th century. And in recent years, this transform is become more and more important because can reduce this kind of Monge-Ampere equation to a linear elliptic system. Okay, so Monge-Ampere equation is fully nonlinear, and it can reduce to a quasi-linear one. So the analysis becomes easy for treat this one. Okay, so in the higher dimensional case, the singular solution constructed by Pogorelov is this form. We see u of x is presented by u x prime xn. X prime is x1 to xn minus 1. And it has this form. Here is 1 plus the square of xn, and here is the absolute value of x prime with this power. And this power is less than 2. So when we check its regularity near the origin in this direction, it is not C2, not C2 or C11. It is only C1 alpha. So it doesn't have the second order estimate. But when we add a proper Dirichlet condition, there is a standard argument of Pogorelov. We can find this type of estimate in these books, Gilbert, Schrödinger, and Gutierrez, and Figari, and also namely the new book also describes this kind of estimate. This is u equals 0 on the boundary, and so this kind of equation, the solution is convex. So u is negative, and minus u is positive. So this kind of quantity with this power and times this one is bounded. So which means this one can be controlled by c times the distance of x to the boundary. So also it is also an interior estimate, but not a pure one. So we only expect the pure estimate in 2 dimensions or in lower dimensions, and in higher dimensions we may expect this kind of estimate because this counterexample. So roughly for a general fully nonlinear elliptic PDE, even in our previous series of those operators, we have a rough idea. We can try to prove pure interior estimate in lower dimensional spaces, like 2D, 3D maybe. So we try to construct singular solutions in higher dimensional spaces. And if we can avoid this by imposing Dirichlet boundary condition, we can prove the Pogorelov type estimate Okay, let's move to the K-Haitian case. The K-Haitian case has the similar conclusion. The first counterexample is in this form. This counterexample, I didn't write it down, but it is constructed by Urbus. When n is greater than or equal to k, and k larger than 2, there are counterexamples for this equation. And but in lower dimensions, just for k equals 2 case, S2 equals 1. When n is 3, when n is 4, the pure interior estimate is proved recently by Guohuan Qiu, just this year's paper, and in 4 dimensions by Schenker and Yuan in 2023 preprint. And when the dimension is greater than or equal to 5, Schenker and Yuan proved that there are also pure interior estimates, but under the condition of this kind of condition, like a dynamic semi-convex condition. But in general, if we remove this kind of condition, can we construct counterexamples for this kind of high-dimensional case? This is a problem. Also, very recently, there's a paper by Siyuan Lu. He considered the Haitian equation, like Haitian quotient equation, like Sn over Sk, and he has 2 conclusions. The first one is k is just between 1 and n minus 3. There are counterexamples. But if k is n minus 1 and n minus 2, there are pure interior estimates. The philosophy is from this kind of observation. Because we, in previous page, we consider S2. S2 is just S2 over S0, because S0 is 1. So this kind of form can be generalized to maybe here is S3 over S1 or S4 over S2, like this. And okay, he proved there are estimates like S4 over S3 is also okay. So this long-standing problem was solved by Lu. While there are still interesting problems left open. For example, if we consider Sk over Sl, but this k is not n, this problem is still open. Okay, let me move to the standard Monge-Ampere case just in 2 dimensions. So how to prove the pure interior estimate? So the first one is the original proof of Haynes, but as I said, it is the proof is a bit complicated. So after maybe about for more than 50 years, Chen Han-O proved the same result, but just using a maximum principal argument. And later, Peng Kuan and Guohuan Qiu also give a new proof, but for the S2 equation. But for the Monge-Ampere, is still the same, still works, also by the maximum principal argument. And recently, if we add a strict convexity condition of U, there are also new proofs of this kind of pure interior estimate. The first one is the paper of Jiapeng Liu in 2021. He used the partial Legendre transform in 2D case But his right-hand side function can be not C2. It's just C alpha is okay. At a new proof just this year is Schenker and Yuan. They use a kind of doubling, and the proof is n for all n. And Y can work in all n because he adds this strict convexity condition. So this condition can rule out that counterexample. Okay, let's move to the last part. This is what we are treating. Okay, we just treat the standard Monge-Ampere equation, and later I will talk about the Monge-Ampere type equation. So this is a result done myself and my collaborator Shi. We consider a C4 function U, which is a strongly convex solution of this kind of equation. The right-hand side is positive, and we assume the f with the power 1 over n minus 1 is C11. And we add another condition. It is a boundary condition like a Dirichlet condition. And the Dirichlet boundary value of U is this W. And the W is larger than or equal to U. And this kind of, we get this kind of estimate. So this estimate is a Pogorelov type because in previous pages I describe minus U with the power times this quantity is bounded. And in this case, because the boundary condition is not 0, so it is W. So I use W minus this quantity, but with a power alpha. And this is not a new result because this result is already proved by Blocky in 2003. But what is new? This quantity is new. This quantity alpha is new. In Blocky's paper, this alpha should be larger than a constant related to the dimension. But in our paper, this alpha can be chosen any constant just greater than 1 is okay. For example, 1.1 is okay. So it has some application. The first one is that we can write this kind of quantity into the distance function. So we have this kind of estimate, just the same assumptions. We have this kind of estimate. So this power is the distance function of the power 2n plus alpha. So the benefit that we can compare with the same type of estimate with Figali. So there is a book by Figali. Its title is Monge-Ampere equation. So he proved this kind of estimate just for the standard Monge-Ampere equation, and the boundary condition is 0. So if we write it as d2u less than or equal to c times the distance function with minus kappa, and Figari's kappa is 3n plus 2, and our kappa is 2n plus tau, and our tau is between 1 and 2. So our tau is less than this quantity, and 2n is less than 3n. So our paper, this exponent is better than Figari's book. But very recently, just last month, there is a new paper published by Nam Li. So he also reduced improved our exponent. So he also have a kappa here, and his kappa is the maximum of n minus 1 and tau. And the tau is any number in between 1 and 2. And in our 2n here, it is only n minus 1. So he claimed that his number is optimal. Okay, let's move to the Monge-Ampere type equation. So I wrote this very old result here, myself and Schrödinger. We are proving this kind of equation, d to u minus a. But this a is generated by a generating function, a gxy. Here, this matrix A is generated by the second derivative of the generating function. So it is also a function of u and du. Under some assumptions, we can also prove the Pogorelov type estimate under various assumptions of this g function. And we have many assumptions, A1, A2, A1 star, A3W, A4W. Very recently, this A4W or A4 star W was removed by Schrödinger himself because he used a kind of strict convexity regularities results of Guilin and Kitagawa in 2017. And our problem is that maybe for some special matrix A, we can treat some marginal case. If the right-hand side is not C2, maybe, for example, we consider the case when the right-hand side B is only Holder continuous in some direction. Okay, so the Pogorelov argument cannot work anymore. So what? How can we do this? And the second problem is if I have this structure from the conformal geometry structure, so can we get the pure interior estimate? So I will main focus on the problem 1, and for problem 2, I will show maybe just one slide, the last slide. Okay, let's see our problem. So our Monge-Ampere type equation, I call it with the partial structure in this form, just adding another term here. But this term is only related to U11, not U22. So if this G is just 0, G function is 0, so it is a standard case. But if we have this one here, we call it the partial structure. And also, we assume the partial regularity for the right-hand side function. That is, phi is C2 in the direction of x1. Phi is only Holder continuous in x2 direction. So this equation can be written in this form. U11 plus C, U22 plus A, minus U12 minus B squared equals delta. Now this kind of equation can be found in this book of Charles. And his book is just a two-dimensional case. If we check this one in this form, it is just the case of B and C equals 0. And A is this minus G times U2. And this delta is phi. Why we call it a partial structure? Because here A is non-zero but C is 0. Normally, when we meet this kind of Monge-Ampere type equation, this C and A are in the same form. Okay, but But now C is 0, A is non-zero, so it is a partial structure. So how we tackle this problem? We write it in the optimal transportation framework using a cost function. So normally, when we treat the Monge-Ampere equation, we always can regard the equation to be an optimal transport problem with cost to be this form. This is called the quadratic cost function. It is x dot y. So in two-dimensional case, it is x1 times y1 plus x2 times y2. So in our partial case, our cost function looks like this. Just modify this x2 to be a function of x2. So once we have this cost function, the OT theory can be applied. But still some obstacle towards the interior C2 estimate. The first one is inhomogeneous term phi has different regularity in two different directions. So for this reason, we cannot rotate the coordinates in the usual way. And also, because of this form, this CXY is not invariant under rotation of coordinates. So when we do this estimate, we cannot rotate the coordinates. It's very harder for us to estimate. However, we have some kind of convexity theory. We call it the C-convex theory. The convexity with respect to this cost function. So in some sense, we can treat this C-convex theory more complicated than the usual convex theory, but the essential is still the usual or normal convex theory. So we do our first estimate, but just the partial one. So the first one is a partial Pogorelov estimate in E1 direction. In our previous estimate, in this part is U naught minus U with the power and times the full Hessian of the U. But in this case, we only have here is U11, no U22 here. Okay, so this estimate gives us an upper bound of U11. But even though this estimate still have some difficulty because we can't rotate the coordinates. But we found that there is an estimate argument used by Savin. Savin have a transform. He can transform the equation. So we are in the optimal transport framework. By make proper adjustments, we can still get this kind of result. That is the upper bound of U11. So next we will want to do U22, the upper bound of U22 or something like that. We need some preparations. That is transforms of the cost or also transforms of the solution. For any fixed point x0, we can denote a point y0. This y0 is a map of x0 because we have an optimal map. TU is optimal map. And we can set C tilde in this way and U tilde in this way. And we can check this form just equal this form. If we add tilde to both U and C, this quantity is equal to this quantity. So when it is positive definite, this one is also positive definite. Then our function is just this function, but this function has some benefit. That is U at this point we choose, it is 0. And also these C functions, C affine functions, are just the hyperplane. So at this particular point, the convex theory is just the convex theory. So next, we will do the partial Legendre transform. We transform this U tilde to be U tilde star by defining it in this way. And when we check the equation of U tilde star, we get this quasi-linear equation. That is phi times U tilde star y1, y1 plus U tilde star x2, x2, and another lower order term. But the previous right-hand side term becomes the coefficient of this quantity. So this is phi. And remember that our phi is Holder continuous in some direction. So it is enough for us to run the Schauder estimate. So we can get the C2 estimate of U tilde star by the Holder continuity of this right-hand side term. So not necessary to differentiate the original equation, just to create this new equation. Okay, there's also some terminology of like the modulus of C convexity, and we can also get a positive lower bound of this quantity. We call it the quantitative restricted C convexity, but I will not mention this too much. And also, we will show this projection of BR is a non-trivial ball, namely that there is a smaller ball belong to this set. Okay. So once we do this, we can know this quantity have a positive lower bound because later we'll use this quantity. Okay, by using the Schauder type estimate, even more we can get the C2 alpha, but just for our use, we just use the C2 estimate. The C2 estimate of U tilde star can be written down like this. And here, it is the L infinity norm of U tilde star. And we can also use this kind of inequality because we can prove this. And so when we plug in some more estimate to the right-hand side, we can get this kind of right-hand side. So here is only the square of radius. And here is that modulus of convexity. So it has a low positive lower bound. So here we can always get the upper bound. So this estimate depends on the gradient of U tilde, also gradient of U du of U itself. So once we achieved these previous estimates, actually we can conclude the second order estimate like this. So by the partial Legendre transform, we can get a relationship of U tilde star y1, y1 equals to 1 over U tilde x1, x1. So because we already get all the full second order estimate of U tilde star, so it has the upper bound. So we can get the lower bound of U tilde x1, x1. So up to here, the partial Pogorelov estimate gives us the upper bound of this quantity. And now this kind of relationship gives us maybe another C, but larger than 0. Okay. So up to now we get the estimate for both directions. And so this is what I explained is just this kind of. And later by just the original equation, we can get this. Okay, I use delta here. Okay, x2, its absolute value is also have the lower bound. And we can use the relationship also from the partial Legendre transform to get this form. Get this form, we can estimate this one. Ux1, we can get this one. Delta x1, x2. So it is equal to x2, x1. Okay, this is the same. Less than equal to C times U x1, x1. Yes. And this quantity we already get his estimate. So we just like a C prime or something like that. So we already get the estimate of 1, 1, 1, 2, 2, 1, and next we need to get an upper bound of this one. So once we get this one, we are done. So this one is actually it is an easier case. Just use the equation itself. Once these are done, this is okay. Okay. So the philosophy is we first get the estimate for this kind of quantity, then we run this kind of argument to get this kind of quantity. So when we get this conclusion, we get the estimate of this. So here is star, here no star, but we still have theta here. But U theta and U is just a transform of the cost function C. So use this relationship, it is easy to get. Okay. Okay. So we get the theta estimate of this partial structure equation. So our main result is this form. The interior soup of this Haitian have the bound C. So this C depends on the C2 norm of F in the x1 direction, but the C alpha norm of F in the x2 direction. So the benefit is that we don't need F to be C2 in one direction. So if our G equals 0, it's a standard Monge-Ampere case. So we can also say our result can be applied to the standard Monge-Ampere case. But our result is weaker than Jackson Liu's result because in his situation he only needed to do in one direction. The other is the same. He has some dual structure of the equation. But our case, if we get this kind of estimate, we can also say this one is the same. But when G equals 0, his estimate is better than ours. Okay, let's move to the last slide. Okay, in this slide, I want to do this equation, like d to u minus a of x times square of du times identity matrix plus b of x times gradient u tensor gradient of u. For example, just equal to 1. Here, this coefficient is important. If a of x is non-negative, or even it is positive and have a positive lower bound a0, this pure interior estimate is trivial, because it can be written in all more transport case, like Mark Tudinger-Wang did in their 2005 paper. So here we want to solve the AX non-negative case. So currently, what we tried is that AX is just 0. It's an easy case. AX is just 0. It's easy case. Even we have this form remaining in this equation, because this term gone and this one is not affected. So we can also treat the A0 case. We can construct a counterexample in higher dimensional case, and the pure interior second estimate in two-dimensional case, just by using a kind of Jacobi identity. This is recently we tried by myself and my students too. So in this direction, we want to tackle the S2 case, not just the Monge-Ampere case, and also the general Sn over Sk case, and also the Sk over Sl case, and also some other kind of combinations. But the most important one is we want to do this problem first, but just the non-negative AX, not just A equals 0. So maybe I will talk to here. Thank you.
Thank you, Professor Jiang. Is there any questions, comments? Okay, for general, well, there are so many general generalizations, but there any great geometry, for example, geometric applications?
You mean the application?
Yeah.
Okay, yeah. These equations are all from those applications. So once these are approved, they can always apply to those geometric problems. Yeah. But the important one is we don't want to assume a boundary condition. Even in my first topic, I still add that boundary condition. But how to remove our boundary condition just to be purely interior? Maybe not any boundary condition, like Dirichlet, Neumann, we don't need that, just the equation. And the second topic is that how to get this F, the regularity of F, we assume a weaker form. If we assume it is C2, so it is an easy case. We just by taking derivatives, so it's always work. So when we cannot derivative the equation, we only need to transform. So in our paper, we transform it to this kind of equation. Even though this quantity cannot taking derivatives, taking two derivatives, but it gets to the coefficient of the main term. In the normal Schauder theory, it is just C alpha is okay, so we can do it. So in this kind of story, the transform is more important than the pure techniques. Okay.
Thank you. Oh, are there any other questions, comments? Share your last point.